Holographic lithography. The next lecture we're going to have after this, we're going to learn how to spatially vary periodic lattices. We know a lot of stuff about periodic lattices and lattice vectors. We will learn how to spatially vary those. This lecture on holographic lithography, I think, is a good practice of grating vectors and wave vectors and how they're related. So I think it's a really good lecture to connect the two, and there's some useful information in here. First, I want to very briefly introduce photolithography. So think of this as photolithography for a non-photolithography person. But a good understanding of that will help understand really what's happening. Then we'll talk about two-beam interference. What happens when we cross two beams? What type of interference does that produce? What can we learn from that? Then we'll generalize that to any number of beams, and we'll be looking at this volume of space where all those beams are simultaneously overlapping. And what we'll find out is we'll get a bunch of dark spots and bright spots, and if we project that into some kind of photosensitive material, we can make three-dimensional structures. So that is holographic lithography. Then I want to step you through what I call beam synthesis. And it turns out we can generate any of the 14 Bravais lattices with even some more freedom than that just by designing 4 different beams coming in at different angles. So how do we design what direction those beams need to come from, what polarization they need to be, how that affects the lattice? That's all under beam synthesis. And then the last thing, I want to show you some work I did in my PhD dissertation called Near Field Nano Pattern that was based on all of this theory. Photolithography. What we're going to do, we have some kind of goop, and it pours like pancake syrup. And it's sensitive to light, usually ultraviolet light, and we will expose it to that light. For what is called negative tone photoresist, wherever the light shines, the stuff will harden, it will cure, and the rest we can wash away in a developer solution. Positive resist act the other way. Wherever the light is exposed, that's where it does not harden, and we can wash that away in a developer solution. So using this, we can make structures with really, really fine features. For this example, we want to make a simple rib waveguide. Well, the first thing we'll do is we'll start off with a wafer. And it's common to, this is a frisbee thing, 4-inch diameter. Notice we have these flat sides, and that's so we can maintain the orientation of this, because a lot of times the structures are too small for us to see. But if we have these flat sides, then we know how it's oriented. So this will be glass, and maybe it's a 0.5 millimeter thick. If we look at a little tiny section of this, so here's the silica wafer, and we're going to spin resist and just be talking about this little piece, this little cross section of the silica wafer, and we're going to grow and fabricate our rib waveguide on top of that. The second thing we'll do, usually using plasma-enhanced chemical vapor deposition, but in some way we're going to grow or deposit a different material on top of the glass. Now, since we want to form a waveguide, we need something with a higher refractive index. So in this example, I'm showing that we've grown this layer, this dark gray layer of silicon nitride, which has a refractive index of about 1.9. The fused silica down here has a refractive index of about 1.5. Then, of course, air has a refractive index of about 1. So we have a high index layer. Right now, it's just a slab waveguide. We want to make it a channel waveguide by making it a rib waveguide. So how do we get the rib in here? Well, what we do now is we spin a layer of this photoresist. This is this goop that is sensitive to light. And we would typically pour this on top of our wafer, just like it was pancake syrup, spin the wafer using some prescribed recipe, put on a hot plate, bake it, and now it's ready to be exposed. So we do that. We put a mask over top. We expose through the mask, so there's shadow regions and bright regions. And depending whether it's negative or positive, we can do whatever pattern we want. We can expose it, we wash it away in developer solution. And so, for example, maybe out here, if this was a negative resist, wherever the photoresist did not see light, it would wash away. And this region here that did see light remains behind, and it's right on top of the silicon nitride layer. So what our next step will do, we'll etch. And in fact, etching is bombarding this with a bunch of particles very fast. So in fact, the resist will etch away too, in addition to the silicon nitride. However, before the resist is gone, it's protecting the center region of the silicon nitride temporarily. So after etching, we get something that looks like this. It has etched away the silicon nitride. It has also etched away the resist, but until the resist is gone, it's protecting that original silicon nitride. And now we can real easily wash away the remaining resist, and we are left with a rib waveguide. That's a real good example of how photolithography works. What we're going to do in this lecture is show you how to generalize this so we can interfere multiple beams, and in this volume of space where they're all overlapping, we get sort of this three-dimensional speckle pattern of bright spots, dark spots. That will expose the resist, and we can form 3D structures doing that. Now we're going to step away from the photolithography, and we're going to talk about what happens when two plane waves cross paths. What happens in that volume of space where those two overlap? The first step in this is to express two electromagnetic waves, and they are passing through the same area of space. So the first wave will have a polarization vector E1, and of course it'll propagate according to e to the minus jk1.r. So k1 is the wave vector of the first beam, and E1 is the polarization of the first beam. Likewise, E2 is the polarization of the second beam, and K2 is the wave vector of the second beam. So the total electric field is simply the sum of those two. And so if we were to plot this in this volume of space where these two waves are overlapping, this is what we see. And we see that we have some really negative spots, that we have some really positive spots. And now let's see what happens next. We need to look at the intensity. So the intensity is the power carried by that wave. So here's what we do. We take our total electric field, look at the absolute value squared, and then just scale it by 1 over 2 times the impedance of the material. But the important thing is that we're squaring the electric field. And when we square this, we start mixing these exponentials and we get trig functions. In fact, we get a cosine out of it. We can group all these terms and express it as something very, very simple. And here's the final expression for what the intensity or the power of two beams interfering looks like. And we see that we have several terms here. We have an overall intensity term, and we can see that's essentially just the sum of the intensities of the two different beams, scaled of course. We have a term called visibility, and we'll see what that is in a little bit. But essentially it's the contrast of the bright and dark spots down here. So we have a visibility term. And what we see is that the visibility has to do with the dot product between the two polarizations. So right away, if the two polarizations are orthogonal, they won't interfere, and the visibility will be very, very low. It will be very hard to even see that we have any of these called fringes, bright to dark spots. If they're polarized similarly, well, this dot product is very large, and we can get a large visibility. Next term is K. That is the induced grating vector. If we look at that intensity that forms from the interference of those two beams, it's a one-dimensional grating, and it has a wave vector, a grating vector, big K. What we'll also notice is that big K and the two little wave vectors form a triangle, according to this equation. And we've seen that before in previous lectures. And also there's a phase offset. In other words, we would be shifting this grating back and forth depending on this phase phi. And that has to do with the phase that comes out of the dot product between E1 and E2. So really in one slide, this is everything about two beam interference. I want to go into a little bit more detail in some other areas. Visibility. What does it mean when we have very low visibility? Well, low visibility, let's say it's 0. I don't see any bright dark spots here. So visibility 0, we get no interference at all. If we have moderate visibility, we can start to see that we have bright and dark spots. However, the dark spots aren't completely dark and the bright spots aren't completely bright. When we have a very high visibility, the dark spots are completely dark and the bright spots are very, very bright. So For holographic lithography, we almost always want very, very high visibility. And remember from the last slide, the visibility has everything to do with the polarizations of those beams, and that will become very important. And we'll talk about how to choose polarizations of the beams that are producing interference. But you can already get a little bit of a taste. We need the polarizations to be similar so that we get a high dot product and we get strong visibility. But as you'll see, when we add more beams, there's actually more to that story. The induced grating vector. So I mentioned real quickly a couple slides ago that the induced grating vector and the two wave vectors of the beams that are producing the interference form a triangle. Another thing we can think of, if we look at our two wave vectors, the grating vector, of course, is going to make a triangle, so it would essentially be connecting these two tips. But notice the alignment of the fringes. They go right down the center of the two wave vectors. So we can see this for many different cases. Now, if we have a small angle between our two wave vectors, we will have interference fringes that are pretty spread out. As the angle increases, we start seeing the periodicity of these fringes becoming smaller and smaller and smaller and smaller. So here's conclusions that I want you to come away with this two-beam interference stuff. The lines of the grating bisect the wave vectors. So look in the upper right here. These gray arrows, those are our two wave vectors. The lines bisect right down the middle. And then, of course, our grating vector is orthogonal to those. And the grating vector and the two wave vectors producing the interference form a triangle. Now, if there's a small angle between the wave vectors, we have a small grating vector, and we're talking about a very long period grating. Likewise, if there's a large angle, we have a large grating vector, and we have a much shorter period grating in the end. So, what is the shortest possible period that two beams can produce? Well, it happens when those two beams are in opposite directions, and we get a very large grating. So when that's the case, we get the shortest possible period, but there is a limit. There is no upper limit. We can always make an arbitrarily long period grating just by having a very, very small angle between the two beams. But there is a limit to how short we can make it, and that happens when the beams are traveling in opposite directions. That concludes the two-beam interference. Now we're going to step through the same math and apply all these same concepts, but now we have more than two beams producing interference. In this case, we have 5 beams, 5 different wave vectors, 5 beams, and we're looking in this volume of space where all of those waves overlap. And we can see we get this very complex, very strange looking overall interference pattern. The form of all 5 beams takes on the same thing. We have a polarization vector and a wave vector for 1, 2, 3, 4, and big N number of beams. So if we have N number of beams, the overall field would just be the sum of those. So just like what we learned for two-beam interference, but we've generalized it now to N beam. And the figure on the right, we're only showing 5. Remember, the next step was to calculate the intensity. The intensity is essentially the electric field squared, the magnitude of the electric field squared. And yes, it's scaled by 1/2 times the impedance of the material where all the beams are interfering. So what we need to do is take the absolute value and square this summation over N beams. When we do that, and there's some algebra here, so I'll just say it is easily shown that, here's our final answer. And it has essentially the same form as we had. We have an overall intensity, and what goes into that are really the intensities of the individual beams. Then we have a sum of a whole bunch of different gratings. Each one of those has its own visibility. So we're looking at the visibility between the I and J beams. And so it makes sense then, the visibility, there'd be a dot product between the polarizations of the I and J beams. Then we have a grating vector, and there'll be a whole bunch of these that come out from multiple beams. And so that's defined the same way. And we also have the phase of each one of those little gratings. And that comes from the phase of the dot product of the electric fields. So it's really the same form we had with two beam interference, but with two beam interference we only induced one grating. Now we're inducing a bunch. And just to give you a picture, on the left and right, this is the same configuration. However, on the left, we're showing field amplitude, and on the right, we're showing the intensity. And we can see some similarities here, but in fact, when you're exposing this photosensitive resist, it's the intensity that matters. Mathematically, we have to go through the field amplitude in order to get to intensity, but in the end, it's the intensity that affects the material. And we call this map of intensity the aerial image. Let's think about the induced gratings. All I've said so far is that if we have multiple wave vectors, we get a whole bunch of different grating vectors. So think of it this way: we pair off, if we have multiple wave vectors, we pair off each of those beams. Each beam produces its own grating vector. So if we only have two beams, two wave vectors, there's only one way to pair that off, we get one grating. If we have three beams, we have three wave vectors, and there's three ways to pair that off, so we get three grating vectors. If we have four beams, and it goes on, and so given big N being the number of beams that we're interfering, the number of grating vectors that we get is n squared minus n over 2. So for example, if we have 5 beams producing interference, that actually induces 10 gratings, because there's 10 different combinations that we can pair off those 5 different beams and get 10 gratings. And you'll see this becomes a problem, and the answer to addressing that ties into choosing the polarization of those beams. But at this point, suffice to say, we have multiple beams, multiple wave vectors that produce even more gratings, because there's many ways to pair those off. So that ends just multiple beam interference. At this point, we know everything there is to know about just the interference of beams. Now we want to take that theory and learn how to make stuff with it. Here's essentially the holographic lithography process. Very similar to what we had making the rib waveguide. We start with a clean substrate. We will spin a layer of photoresist. We will choose a group of beams, all at different angles, with different polarizations, and we'll interfere them within the resist. And this produces an aerial image, this three-dimensional speckle pattern with bright spots and dark spots. Well, after this does chemical changes to the photosensitive material, we get what's called the latent image. And the latent image is more a chemical thing, the aerial image is an electromagnetic thing. But ideally, the aerial image and the latent image are the same. I won't get too much into it in this lecture, but there is some diffusion mechanisms, and the latent image tends to be a little bit blurred version of the aerial image. Then we put this exposed resist into a developer solution. It's another liquid that dissolves away the stuff that has not been exposed to light, assuming we had a negative resist to start with. And what we're left with is something three-dimensional, a photonic crystal, a metamaterial, really whatever it is we want to be. That's holographic lithography. The most famous configuration of beams for holographic lithography is 4-beam interference. So that's what we're going to talk about most here. So first, if we interfere 4 beams, we get 6 gratings. And we can look at that by pairing them off. If we look at the interference between beams 1 and 2, we get a grating vector. We'll just call that big K sub 1, 2. We can pair off 1 and 3 and get a big K 1, 3. We can pair off 1 and 4, 2 and 3, 2 and 4, 3 and 4. And so we get 6 different grating vectors. Now, we could say, well, what about the interference of K2 and K1 the other way around? And we would get a minus big K21, but that's the same thing really. It's just K12 because we're only looking at the power. So in fact, we could in theory, describe also these, but this K2 one carries all the same information of the K1 2. And so this is redundant. We only need one of them. Doesn't matter which one, but this is the standard. Take this combination. So these other ones we ignore simply because their information is already contained over here. So the interference between beam 1 and 2 is the same as the interference between beam 2 and 1. What we want to do now is, given our 4 beams, we want to figure out what type of lattice will that make. So if we back up a few lectures, we know that all 14 Bravais lattices can be described by 3 grating vectors. And those were the reciprocal, the primitive lattice vectors of the reciprocal lattice. When we have the interference between 4 beams, we actually get 6 different grating vectors. It turns out we only need 3 of them to determine the symmetry of whatever it is we're making. The rule is, though, the 3 that we choose have to include information from all 4 wave vectors. And as long as that's the case, the 3 grating vectors that we've chosen will be the primitive reciprocal lattice vectors of the lattice that we would be making by this holographic lithography process. So for example, a very common choice is big K12, big K13, and big K14. And we can look at the wave vector combinations that produce these 3 grating vectors. And we see all 4 wave vectors here. Another perfectly valid choice is big K12, big K23, and big K24. All 4 wave vectors are here, another valid choice. And these would still be the reciprocal lattice vectors of the lattice that we would be making. Well, here's an incorrect choice. Big K12, big K13, big K23. And why is this invalid? Well, where is K4? We're missing information from the 4th wave vector. The 4th beam hasn't been considered here, so this is not valid. But either of these first 2 cases are valid choices, and we can proceed with these grating vectors to figure out the symmetry. So a big conclusion is that we can choose 4 beams, and the interference between those 4 beams, it turns out we can produce any of the 14 Bravais lattices. That's pretty cool. So we showed you very quickly that we could go from the 4 beams, choose a set of 3 grating vectors that use information from all 4 beams. Those are our reciprocal lattice vectors of the lattice we would be making, and we can figure out the symmetry. But what about the other way around? What if we start off saying we want to create a photonic crystal with face center cubic symmetry? What 4 beams do we need to do that? So we call that beam synthesis. Now, one neat thing that I think I was the first one to discover or explain is that forming photonic crystals with holographic lithography, we almost always get a chirp-looking lattice. Notice there's a higher fill fraction up here than down here, and that's because this lattice was formed with beams going from the top down. And the resist absorbs the light, so there's just more light up here than there is down here, so we get thinner, sparser features. And through a bunch of theory, I was able to explain that. But the point is, with holographic lithography, because the beams get absorbed through the resist, there's always going to be some kind of chirping. Now, we can work on resists that are what are called higher contrast, and that can combat that, but I think there's always going to be some kind of chirping. With that said, let's dive into beam synthesis. So here we're starting off with which lattice symmetry we want, and I'll say hexagonal or body center cubic, and we can go through a set of steps and we can figure out what those 4 beams need to be in order to get that symmetry that we want. Step 1, let's design the unit cell. And here's one of the only applications where I actually like to use the axis vectors. So these are the ones, these are not the translation vectors, these are the axis vectors, and they point along the perimeter of the conventional unit cell. So if I want something with cubic symmetry, then I would want the first axis vector to be lattice spacing in the x direction, the second one to be the lattice spacing in the y direction, and the third one to be lattice spacing in the z direction. this would make a cubic photonic crystal. Now there's not enough information here to say simple cubic, body centered, or face centered. So I'm just using this to orient the unit cell and to size it. The next step will figure out the translation vectors. And we presented these equations before, but now given the symmetry and those axis vectors, we can calculate our translation vectors. So for example, if we wanted face-centered cubic, we already have our axis vectors for cubic symmetry. Then the first primitive translation vector would just be 1/2 of the second axis vector plus 1/2 of the third axis vector, and so on. So now we would have the 3 translation vectors of the lattice that we want, and that does uniquely describe, the translation vectors uniquely describe all 14 Bravais lattices. If you're smart enough, maybe you could just start here with the translation vectors. I like to start with the axis vectors because it's more intuitive with the size and shape of the unit cell, and then do this quick step to get to the translation vectors. Next step is to calculate the reciprocal lattice vectors. So that's pretty easy, we've done that already. Let's start an example, and let's say, and as I step you through each of these steps, we'll keep adding on to this example, but let's say we want to create a face-centered cubic photonic crystal. We will choose how to orient our lattice, and we will then calculate the the direct lattice vectors. These are the primitive translation vectors of the direct lattice. So if we plug in our standard axis vectors, these are the reciprocal lattice vectors that we would get. And here, our first axis vector is just lattice spacing in the x direction. The second one is just lattice spacing in the y direction. And the third one is just lattice spacing in the z direction. And here we come away with the 3 translation vectors. Next, we want to calculate the 3 grating vectors. And here's an additional step that I've added. But normally the connection here is that grating vectors and translation vectors are the same thing. So it makes sense if we've just calculated our 3 reciprocal lattice vectors, let's just make those the grating vectors. And it turns out there's actually some reasons we want more freedom than that. And so what we can do is we can have a column vector of our translation vectors. We can have a 3x3 matrix of integers. And then we can have our grating vectors. And we're going to fill this matrix Q just with integers. Now there's some rules here. Each lattice vector has to be used at least once. We can't ignore them, which means that there's no columns in that Q matrix that can be all zeros. Also, each of our grating vectors, A, B, and C, have to be unique. So there can't be any row in Q that is some integer combination of the other rows in Q. So they have to be unique. So the easiest choice of Q is to do the most obvious thing, and we'll just say that the grating vectors are those translation vectors that we calculated. But I do want to point out that is not the only option, and we'll come back to why we want more freedom here in a minute. Now, we have 3 grating vectors. We're after 4 beam interference. 4 beams actually produce 6 grating vectors. And so we pair them off and we get our 6 grating vectors. In a few slides ago, we could choose a set of 3 that used information from all 4 wave vectors. So the question is, what's the relation between the little k's, the wave vectors, and the big k's, the grating vectors? How do we choose that? It turns out there's 120 possible combinations. But there's a lot of redundancy in that, and in fact there's only 5 that are unique. So what are the rules to come up with this unique way that the wave vectors will relate to our grating vectors? One, we know this one already, but the grating vectors have to contain information from all 4 wave vectors. The other thing is the choice of how the grating vectors relate to our wave vectors has to be unique. If there's any redundancy in there, that doesn't count. So for example, this first set of 3 grating vectors, and they're implying already the relation between the grating vectors and the k vectors by these subscripts. This is a valid choice, we've already talked about that. Well, what about this one? It turns out this is valid, we could choose this, However, it's really the same thing as this first configuration. All we did was exchange integers 1 and 4. Everywhere we saw a 1, we put in a 4. Everywhere there was a 4, there's a 1. So in fact, this really is the same configuration. So we ignore that. And by following these two rules, we can whittle down our 120 possible ways that the grading vectors can relate to the wave vectors down to just 5. And that is very, very useful, because if we're exploring all the different options, there's only 5 we have to explore, not 120. So here they are. And I put a lot of work into figuring this out, and here it is. So those are the only 5 that we have to explore. Now I can say the most common choice is this K12, K13, K14 combination. That's by far the most common choice, and that's this first one. But we could also choose these last 4, and there's consequences of doing that. Once we know that relation, now we need to calculate the 4 wave vectors, and this isn't so easy. Right away, we know how our wave vectors are relating to our grading vectors because we've just chosen that. However, we know 3 things right now, but we're trying to calculate 4. So we have more unknowns than we have knowns. So what do we do? Where does that information come from? Well, it turns out, since we are probably doing holographic lithography with a single frequency or single wavelength beam of light, we know that the magnitude of all of the different wave vectors have to be the same because it's the same wavelength of light. So here's our 4th equation. However, this is not a linear system of equations, so we can't solve it linearly, unfortunately. And so we end up solving this numerically instead. But notice, if somehow magically we knew one of the beams, we can immediately calculate the other 3 wave vectors from it because we already know the grading vectors. And if, let's say the first wave vector is somehow magically known. Let's look here. If the first wave vector is magically known, we know the grading vector, we can calculate the second one. And we can calculate the third one, and we can calculate the 4th one. So really, all we need to do is somehow guess at that first one and test it. So we initialize our algorithm, we make a guess, we calculate the other 3 wave vectors, and then we check if the magnitudes are all equal. If they're all equal, there's only one answer here, we're done. If they're not, we need to somehow adjust that first K1 in an intelligent manner. And this is an iterative process. We can use something like gradient descent, but we somehow adjust that K1 and we try it again. We calculate K2, 3, and 4 and check the magnitudes. And we keep doing this until all the magnitudes are the same, and then we're done. So if we look at this, here's our space, and here's how we get the 3 axes represent all our choices for the 3 different components of K1 and what the error would look like. We're trying to minimize the error. So we're trying to get the dark blue, if you will. And that's the valid choice for K1. So this is a pretty smooth, continuous solution space, and the conclusion is we can use something like gradient descent. We'll make a guess somehow, and we'll use gradient descent or a similar optimization algorithm to tweak that value of K1 until all the magnitudes are the same. So it's a numerical process, but we can do it. It's pretty easy, and we can calculate the 4 wave vectors that will give us those 3 grading vectors doing this. So let's continue with our example. We know our 3 grading vectors. We've chosen how that will relate to the 4 wave vectors. And then from work on the previous slide, it turns out in this case we can come up with some closed form equations. Here's what our 4 wave vectors need to look like. These 4 wave vectors will induce 6 gratings, and 3 of them will be the reciprocal lattice vectors that we're after. A good question that might come up now, what happens to those other 3? And we need to talk about that. First, we need to relate our exposure wavelength to the period of the lattice that we are inducing. So let's remember, the magnitude of all of our wave vectors are the same. So we can just write it as magnitude of K. They're all the same. They're in different directions, but their magnitude is the same. And that is simply just 2 pi over the wavelength. In in the photosensitive material, or 2 pi times refractive index of the photosensitive material divided by the free space wavelength. So this really is the equation where everything comes from. It relates our free space wavelength, the magnitude of our wave vector, and the refractive index of the material, and that's what we'll use. Now from the previous slide, we found that the magnitude of our wave vectors relative to the lattice spacing is this. Now we can use this to figure out, either given a free space wavelength, what lattice spacing that will produce, or if we really need to realize a certain lattice spacing, what wavelength we would need to do that. However, usually in lithography, the wavelength of our exposure is fixed, and there's a lot of reasons for that. The lamps sold only generate certain ultraviolet lines. Also, the resists that we use are usually only sensitive over a relatively narrow range of wavelengths. So usually the free space wavelength is fixed. And we can fill in here now, we can put 2 pi n over magnitude of k, and then we have an equation that relates the free space wavelength and lattice spacing to refractive index. And here's what we can use to do this. Now let's say 365 nanometers is our wavelength. We will plug that in for wavelength here, and really just using this equation above, what we get is that the lattice spacing is 1.789 nanometers. So in other words, for this particular choice of 4 beams, and we expose with 365 nanometer light, we get a lattice spacing of 1.79 microns. So a question can come up, well, what if I want 1.5 microns? Can I not do this? We're probably not free to change the wavelength. If we go back, I pointed out a few places where there's some degrees of freedom. There's that matrix Q, we can choose different integers, and then we had our relation between the wave vector and the K vector. So those two areas gives us some degrees of freedom to choose different combinations of wave vectors that still give us the lattice symmetry we're interested in, and each of those lattices may have a different lattice spacing that could work for us. So already, there's one reason why these degrees of freedom are useful. Now, once we calculate our beams, in this particular case, if we look at our X, Y, Z axes, we can see all of the various different stages of our result here. So the red lines were the original axis vectors. That showed us the size and orientation of the unit cell. Then we calculated these translation vectors. Those are of the direct lattice. We reciprocated those, and we got these green lines. Those are the reciprocal lattice vectors now. Then given those, we chose how they related to the wave vector. We chose the combination, the matrix Q, and we ended up calculating 4 wave vectors. Now notice we have essentially a center beam surrounded by 3 beams radially distributed around that. But notice they're all kind of going off on this diagonal. Now that may or may not be convenient for us. So very often we want to reorient the beams so that it's a little bit easier to realize in the lab. So one thing we could do is reorient the beams so that central beam is along the z-axis. So in the upper left, this is where we were on the previous slide. We reorient the beams and we end up here. The only problem in doing that is the resulting lattice is reoriented in the same way, and that may or may not be a problem with us. If it is a problem, then we're not free to reorient the beams. If it's not, maybe we have something with already a complete band gap, so it has a band gap in all possible directions. It doesn't matter how we orient it, and we're free to do this. The last step, now that we know the directions of our 4 beams, is to choose the polarization. Now, at some point in this process, we chose how our wave vectors related to the 3 reciprocal lattice vectors. And we said that those 3 reciprocal lattice vectors are grating vectors. So what I'm showing in green here are the ones that we chose to work with. These other 3, remember 4 beams actually induce 6 gratings. These were the 3 that we ignored. What we usually want to do with polarization is choose polarization such that the visibility of these 3 gratings is very high and the visibility of the other ones is very low. If we are able to do that, then these 3 gratings disappear, and we get really just the sum of 3 gratings, and that gives us a very nice looking lattice. That's ideal. We can't always realize that. So let's think about the polarization of this exposure configuration. And it turns out, for face center cubic, this is the famous umbrella configuration, we have a central beam with 3 beams radially distributed around it. And the angle between these 2 beams is 120 degrees. They're evenly distributed. And the elevation angle of those side beams is 38.94 degrees. So how do we choose polarizations? Well, the 3 grating vectors we chose, in fact, it turns out it's pairing off between the center beam and this side beam. That produces a grating vector that we wanted. The center beam and this side beam, that's another grating vector we wanted. And the center beam and this side beam, that was another grating vector we wanted. However, the side beams we can also pair off, and they would induce gratings. So we want to minimize the interference between the side beams and maximize the interference from the side beams to the center beam. So how do we do that? Well, these side beams are almost at 90 degrees with respect to each other. So if we make them linearly polarized in their planes of incidence, their polarizations are almost at 90 degrees again with respect to each other. So their dot products will be very close to 0, and the visibility produced by the gratings from the interference of the side beams will be minimized. Well, we know that linear polarization and circular polarization, they do interfere quite well. In fact, we get very high visibility gratings pairing the center beam off with each of the 3 side beams. So we've chosen polarization taking the information on the previous side into account. So here's the result. The first image in the upper left, this was our electric field. From this, we calculated the aerial image. This is the intensity profile. And then from there, we did holographic lithography. Here is the face center cubic lattice that we would get having done that. So there's our final lattice using the famous umbrella configuration. And folks in the literature have made that lattice many times over. Let's look at the impact of polarization. So doing what we did on the previous slide, here's the lattice that we get. The famous umbrella configuration, center beam being circularly polarized, side beams being linear. Here's the lattice we get. That looks really nice. If we made all beams have circular polarization, now the side beams are also producing reasonable interference. Well, we still get something that's periodic, but clearly it does not look as good as this first one. And that's because we really have 6 gratings all superimposed here. We really only wanted 3. If we made them all TE polarization, so they're all linearly polarized, here's the lattice we get. If we made them all TM polarized, here's the lattice we get. And again, we keep coming back to this first one, this umbrella configuration, looking the best. So usually we want to maximize the visibility of our 3 chosen grating vectors and minimize the visibility of the 3 that we ignored. Usually, that may not always be the case. So here's some final notes to come away with holographic lithography. So, unlike what you'll read elsewhere, this beam synthesis procedure is unique in that I've identified 2 areas where there's more freedom than we would realize. And that was the relation between the wave vectors and the grating vectors, and also how we related the grating vectors to the reciprocal lattice vectors. That's where we use the matrix Q. So we can use that to explore many more options, and we can use those options to realize different lattice spacings, or maybe there's a beam configuration. Maybe we can only have beams coming from one direction and within some narrow cone of angles, or maybe there's some other constraints just due to how things are set up in the lab. And we can use these degrees of freedom to explore all the different possibilities and hopefully get something that works for us. We also talked about beam reorientation and beam polarization and how we choose that. So we use all this to come up with some setup in the lab that works the best for us. Last subject here is something called near field nano patterning, which is one of the things I did when I was getting my PhD. So what is this? Well, it is holographic lithography, but there's a big problem with holographic lithography. When we interfere those beams, if there's any vibrations, then that aerial image moves around within the photoresist and it blurs. And in fact, it is really difficult to minimize the vibrations enough to do holographic lithography very well, without a very expensive setup. So instead, what if we use diffraction to produce our 4 different beams? So we would come up with some kind of phase mask. So this would be a bunch of grooves etched into glass that we would put in direct contact with the resist. Then, when we expose with a single beam, this would diffract into our 4 beams, or however many we wanted. That would form our aerial image, and we follow the rest of our lithography process, and we could end up with a 3-dimensional lattice at the end. Now, the advantage of this being in direct contact with the resist is that if there's any vibrations, the mask is in direct contact. That aerial image walks or vibrates with the resist. So there's a lot less blurring. So here's a movie that I made of the near-field nano patterning process for your enjoyment. Here it goes. Onward. So here's the benefits as I see of near-field nano patterning. The 2 big ones that stand out in my mind. One is that it's very, very immune to vibration. So in fact, suddenly we can do holographic lithography without really worrying too much about the vibrations. Another neat thing, since we're using this grating that diffracts the 4 different beams, they really don't separate from each other that far. So the light does not have to be that coherent. And in fact, what I've shown in my research is that we can produce very usable interference just with a lamp, which is crazy that we could even think of doing holography or anything holographic with a lamp. But that's just because the beams don't separate that far. The light does not have to be that coherent. Now, it's extra challenging because this diffraction grating probably produces more than 4 beams, so we need to control the pattern on the grating to really optimize the polarization and the intensity in our 4 desired beams. And so, but knowing all this other stuff, we could use that freedom to in fact do a much better job of designing those types of diffraction gratings. So here it is. Here's atomic force microscope images of these lattices that we made. And as far as I know, these were the first photonic crystals made just using a standard lamp with this near-field nano patterning. And what enabled it was that this grating in direct contact with the resist made it really immune to vibrations. We put this in a standard mask aligner, didn't do anything about vibrations, and it worked really well. So that's holographic lithography. I think this is a great exercise of lattice symmetries and grating vectors and wave vectors. It's kind of weird, but I just think it's such a great example of how all this stuff is interrelated and some neat things that we can do with it. So that ends this lecture.